the number of participants is quite high in this school. And I would like to thank all my co-workers for the help they have provided to prepare this series of lectures. And today I'm going to discuss, to present incompressible linear elasticity for mixed finite elements and using also block solvers. So during this presentation, I'm going to briefly introduce the standard linear elasticity finite elements and discuss the inherent problems that are coming with them regarding incompressible linear elasticity. Then also the mixed formulation the mixed formulation that is bringing in the resolution of the problems that bring the incompressible linear elasticity. Also, Taylor-Hood and Crouzeix-Raviart elements are presented regarding the mixed formulation, and stability, energy spaces, the patch test, and the inf-sup conditions are presented and briefly discussed, as this is a very deep problem that deserves a lot of understanding. Then I'm going to show you some things regarding the MoFEM code that is used throughout the tutorials, some general features of it. And finally, I'm going to show the convergence for a particular problem of linear elasticity, a compressible linear elasticity for Taylor-Hood and Crouzeix-Raviart elements, and the possibility of using the block solvers for this class of problems is going to be briefly discussed. So to begin with, I would like to have a brief discussion regarding what is a coupled problem and what is a mixed formulation, because sometimes they are mixed, they are referred for the same thing. So regarding the coupled problem, when we consider coupled problems, there are two or more problems that are described by differential equations that they present different physical behaviors. Of course, for each equation, there is a different variable, at least one, and they can be describing thermal conductivity and elasticity, electric conductivity and elasticity, again, two equations, fluid structure interactions, magnetohydrodynamics, and other examples. However, on the side of the mixed formulation, again, we have at least two unknown variables, as it was in the coupled problem case. But in this case, the extra variable is not coming from a different physical problem. It's coming as an extra constraint or equation that offers this extra variable that is called the auxiliary variable, in order to give extra features for the solution of the particular physical problem we have in mind. Some examples can be incompressible elasticity, that's going to be presented in this lecture, Navier-Stokes equations, convection reaction diffusion, contact problems, and even the thermal problem can be described as a mixed problem, and that is going to be discussed later on by Andrei. So, yes, standard problems that usually engineers are used to solve with one equation and one unknown variable can be transformed into a mixed that reminds us a coupled problem, because there are two unknowns, yet is not they are not listed as coupled because they have this extra auxiliary variable for the same physical problem. So some motivation regarding why to use the mixed formulation. As I said, it gives some solutions that cannot be sought by using standard formulation, for instance, incompressible elasticity and fluid flow. And also for contact problems, they offer quite robust solutions. especially in the incompressible elasticity, they offer accurate computation of stresses without special assumptions. And two other things that I don't want to really talk intensively about is the possibility of having different formulations where we can choose the regularity of our solution. And also we can add a posteriori error estimators in order to improve the efficiency of the solution. These are things that are going to be discussed in more detail by Andrei in the next lecture. So I would like, as I said, since we are adding an extra variable, there are extra complications regarding the assumptions and the tools that we need to use in order to solve these problems. And for this, we need to have a better understanding of the functional spaces. So here I'm going to give a brief introduction for the two main functional spaces that are going to be used in the present presentation. And this involves the Lebesgue space that is presented as L2 in the domain, where is the set of functions that fulfill this inequality, where the integral of the squares of the functions gives us the norm, and this is the norm squared, sorry, and this is always a finite number. So this integral will never blow up. This is like all these functions that have this attribute. And this is the L2 norm. And then regarding the second space that we are interested in is the Sobolev space H1, where this is the space of functions who are already in L2, as presented here, but also the integral of the square of their gradient is finite. So, in other words, is the set of functions that both the functions themselves and their gradients are in L2. And here is like a more general relationship between the norms of these two functional spaces, where they have this neat relationship. And you have to just appreciate the fact that these are different norms. So they, every time that we define, we refer to this norm, they present a different value, as these right-hand sides are different. So let's begin with the standard formulation for linear elasticity. So for those who are doing solid mechanics, they are fairly accustomed to this system of equations, where the continuity equation is described by the first relationship, and then the boundary conditions for tractions and displacements are presented by the other two relationships. And here, for the purpose of this presentation, we are going to use the Cauchy stress presented by the Lamé decomposition, where you can decompose the stress into a volumetric and a deviatoric part. The strain tensor here is defined as this, is a symmetric tensor, and the pressure is defined as the product of a material parameter, lambda, times the trace of the strain, and this lambda is so-called the first Lamé parameter, and is defined with respect to Young's modulus and Poisson ratio. And the second parameter that is involved in the deviatoric part is also defined like this, and is called the second Lamé parameter. So in order to bring in the finite elements, what we need to do is to multiply the conservation of linear momentum relationship by a function, a test function, that is going to be in H1 space, and integrate both sides. So the relationship becomes like this, and this has to hold true for any chosen test function that is in this space. So what we do in order to end up to the weak formulation is that we integrate by parts the part where essentially there are two the second derivatives of the test function hidden under these brackets. And by performing this integration by parts, we recover the standard weak form of the linear elasticity relationship. And if we plug in the Lamé composition into stress, we're going to get this relationship now, where the volumetric and deviatoric parts are decomposed. And you have to just appreciate that this is the standard, it's equivalent, full equivalent with the standard expression for linear elasticity, where D is the elastic stiffness matrix. But what happens when we consider incompressibility in this case? So incompressibility is when the Poisson ratio is equal to 0.5. So no volume changes can occur. And this means for the first Lambert parameter that at the limit of 0.5 of the Poisson ratio going to 0.5, this term tends to 0. Therefore, the whole term tends to infinity. So we have on the left-hand side an infinity term, whereas on the right-hand side, because these are the boundary terms or body volume term, they are finite. So we have something finite equal to something infinite, and this cannot be solved. Usually the remedy is to use nu very close to 0.5. And another idea would be maybe to divide both sides with lambda, so that on this side it will get equal to 1, and this side would be 0, but also on the right-hand side, we would get also 0. So we would have nothing to solve. So for this, in order to tackle this corner case, a different approach has been proposed, and this is the mixed formulation for linear elasticity, where now we have a different statement. We're not interested only to solve the conservation of linear momentum, but also we add a new parameter, pressure, that has to fulfill this relationship that is essentially being equal to the volumetric term of the stresses. And this is added like an auxiliary parameter, as I said earlier, and sometimes is considered also as a constraint. So again, the Cauchy stress is decomposed, but now this parameter is not calculated in the first equation through this relationship, but is kept as an auxiliary parameter. And in the second equation, we introduce the relationship of the pressure and the trace of strains. So again, like we did for the standard formulation, we multiply both equations with test functions. And this is how it looks like. So after implementing the integration by parts for the term in the first equation. And as you can see here, we are testing the second equation, not with the previously used test functions for displacements, but with pressure test functions. And we can have a choice between H1 and L2. So depending on which choice we make to test the second equation, we would have a different flavor of the mixed formulation. So the statement for this mixed formulation is to find a U or P that is either in H1 or L2, such that this system of equation is fulfilled. And we can go on for finite elements in order to be able to solve this. This is now in the continuum setting. We want to discretize this. So we can discretize the two fields, one being the displacement field, and the other one being the pressure field. You can see that pressures are scalars, and therefore, for the displacement, the unknown, the coefficients that are here presented with tilde, are going to be depending on the dimension, either 2 or 3, or 1 in one-dimensional case, and pressures are going to be always scalars. So there's always one unknown corresponding to the same shape function, where there are 2, 1, 2, or 3 for the displacements. And then the global system of equations would look like something like this. Now, as I said before, what is brought by this formulation is that we can deal with the incompressibility. And this is what I'm going to describe now, is that we can divide the second equation by lambda that tends to infinity. So when lambda tends to infinity, this term will tend to 0, and therefore this term will become 0 as well. So in the first equation, lambda is omitted, so there is no infinity at all present. And in the second equation, the term that has lambda can become 0, which is a finite number. And here you can see, as I said, the system of linear equations. And yeah, as I said, when lambda tends to infinity, it becomes a saddle point problem because this matrix is equal to 0. And the definition for each matrix is presented here. This one is with respect to the displacement field only. This one is the off-diagonal term related to only pressure. And then we have the off-diagonal terms that are coupling displacements and pressures. And the right-hand side boundary conditions. So if we inspect the matrix's dimension, we're going to see that A is have the dimension both on rows and columns equal to the number of unknowns of displacements. For B is that of pressures, and C is like a mixture because the number of rows will be different than the number of columns depending on the choice of unknowns. And you can see how it looks like. So here is the number of U, and here again the number of U unknowns, and here the number of P and the number of P. So we think that, okay, if we just add this extra equation, we can solve incompressibility at a first glance. But if we look a bit deeper, we are going to understand that the things are not as simple as they seem. So in the extreme case where we take into account incompressibility and 0 is present, we can perform elimination of one unknown by taking into account this multiplication. And by solving, multiplying this, there is a relationship where involves only U tilde. And by solving for U tilde and taking into account the other multiplication, we can end up into another single unknown equation. However, this equation involves, to solve this equation, involves two inversions. One being a matrix, and the other one being the multiplication of these three matrices. So in order to be solvable, we want A to have a rank equal to the number of rows and columns because it's a square matrix. That when rank is equal for a square matrix to the number of rows and columns, it means that it's invertible. And more about rank is going to be discussed in a bit. And also the rank of H, that H is what is within these brackets, has also to be equal to NP, because if we do a dimension analysis here coming from the multiplication, we see that eventually H is has the number of rows and the number of columns equal to the number of degrees of freedom of the pressure field. And from this, as I'm going to explain in a bit, we know that the number of unknowns for displacement have to be at least larger or equal to the number of unknowns for the pressure field. However, this is a necessary relationship that has to be fulfilled, but is not sufficient. And we're going to discuss a bit about that as well. So in order to have a chance to solve this problem, we definitely need to fulfill this relationship. So in order to explain you why we need to have this relationship, I'm going to just give a brief introduction on rank relationships. And you can think of a matrix that is of m by n columns. It doesn't matter whether it's a square or not. The previous two matrices we discussed, they were both square matrices, but in order to do the analysis, we have to take into account also rectangular matrices in order to understand this feature. And it can be either tall and wide, or short and wide, or tall and narrow, or even a square matrix, where the relationship on the rows or columns, you can see them on the bottom.
Ignatius, sorry to jump in. Would you want to take a questions right now? We have one of the participants with the raised hand.
I don't have a problem as long as we can keep it brief. I'm okay.
Let's unmute.
Can you hear me?
Yes, we can hear you. Yeah.
Yeah. Ignatius, could you please go to the previous slide?
Yep.
So here, since you already wrote on the previous slide that F2 is 0, so in that case, I don't understand what will the first equation bring us.
Okay, I agree. This is just something that it's in order to understand the solvability of the system. Because eventually, yes, you are going to get something like this. If it's 0 or not, you know, this can go to 0 and we'll keep...
Yeah, that's fine. But if F2 is 0, then the first equation tells me that I'm looking for like a, I don't know, null space of a matrix, which is...
I agree, yes.
Non-singular.
Yeah, that's true.
That could be infinite number of solutions to that.
Okay, this is yeah, I agree. But as I'm going to discuss later, there are relationships that dictate that there are unique solutions. These are called the inf-sup conditions for this particular set of equations, regardless of whether that is 0 or not.
Okay, so you just put here, you put like not a 0, but F2 just for the sake of, let's say, the analysis.
Yes.
Okay. Yeah.
Thanks. Yes,
Thank you.
I had that in mind. Thank you for the clarification.
Thank you.
Okay, so yes, so the rank of a matrix is the number of linearly independent rows or columns of this matrix. And based on this virtue, the rank of a matrix P is always smaller or equal, at best equal, to the minimum of the number of rows and the number of columns. And in order just to have a better understanding, because maybe this is coming out of the blue, I'm going to just give an example, 2 examples of a matrix that has 5 rows and 2 columns. So here we have a matrix that you can see that the first 2 rows are linearly independent clearly, as whatever multiplication I apply to the second row, I will never recover the first row, and vice versa. And therefore, the number of linearly independent columns is identical to the total number of columns, because whatever I do to this vector, I will never, as a multiplication, I will never recover the second one. However, and therefore, we see that the rank of P is equal to 2, that fulfills this relationship. In the second case, all rows, actually I just showed 2, but all rows are linearly dependent, and also both columns are linearly dependent. By the way, I wanted to say that there is no point of checking at the rows whether there are more than 2 linearly independent vectors, as an R2 space can be described only by 2 vectors. There's a third vector will never bring extra information. So that's why we stop there. Whereas here, we see that they are linearly dependent, and therefore, the rank of this matrix is 1, that fulfills again this relationship. And in order to end up and understand this analysis, we have to refer to a general relationship of rank of general matrices, K and L, where the rank of this multiplication is smaller or equal to the minimum of each individual rank. But because here we take into account a matrix that we a priori consider that is full rank, A minus 1 and A are both invertible, in order to understand H, whether it's invertible or not. And for this particular case, when one of them is full rank and square matrix, the rank of this multiplication is equal to the number of unknowns of this square matrix. So in order to understand what is the rank of H, we substitute H here by the multiplication. We can consider only the right two multiplicants as one part and the left one as another one, and consider this as a multiplication of two general matrices like this, and therefore the first relationship holds. But we can see from the second relationship that the rank of this multiplication is essentially equal to the number of unknowns. And if we substitute the general relationship for CT, we end up with, for the left-hand side of this minimum, with the minimum of the number of rows and columns of this matrix, that eventually ends up with the number, with the minimum of either the number of pressures or the number of unknowns of displacements. So from this, we understand that if we want to have a chance to solve H, we have to have NU greater than NP. Because if NU is smaller than NP, it's going to be less than, so the minimum of this will be equal to NU, that is bringing the rank deficiency of H. So only if this relationship hold, we could search for inversibility of H, and therefore we can have a chance of a solution. But this is not the whole story for this. Still on the inversibility of the matrix, we need to have a check for the patch test, the so-called patch test. And in what I'm going to present, this is going to be a schematic representation of a part of a mesh, where the three degrees of freedom for displacements are presented with open circle and open square for pressures, and as closed, these are the prescribed displacements. And here you can see a Taylor-Hood element for orders 1 and 1 for displacements and pressures, where nothing is prescribed. And we can then see that the NP is equal to 3, and NU is equal to 6. NU is greater than NP, so this test has passed. H is invertible. But if we consider a different case where a domain, a triangular domain, is discretized by only this element, and we want to constrain the displacement on one side, we can see that the number NP is 3. But now, because these are constrained unknowns, they are taken out of the system of equations. This is how we deal with essential boundary conditions when we solve the problem. And therefore, the total number of unknowns that is remained in the system of equation is 2. That is less than P, and therefore, the patch test is not passed, and this is not a solvable problem. So instead of keeping it like this, we can bump up the orders for displacements. And now we have degrees of freedom also on the edges. The problem still remains the same. We want to prescribe one boundary of this element, which is the whole domain. And now if we do an analysis, of course, the number of degrees of freedom for pressures stays the same. But for displacement, it changes. Now we have 6 nodes, and 3 of them are prescribed. So we have in total 6 free unknowns, and 6 is greater than 3, so the test has passed. But now let's consider a case where we want to prescribe the whole boundary. What happens? Well, still pressures. We cannot prescribe pressures in this kind of problems because they cannot admit boundary conditions, essential boundary conditions. So in this case, the number, sorry, here should be 0. The number of NU is 0. And therefore, the test is not passed. So for this, we can increase the, we can refine the mesh in order to have more elements. And we can see that if we have more elements where each one has a second order approximation on the displacements and the first order approximation for pressures, we get some free degrees of freedom for displacements. And if we count the number of degrees of freedom of pressures, we have some extras as they appear on the extra nodes that are coming from the extra triangles that we have in the discretization. And then if we count the full number of nodes for displacements and subtracting the number of prescribed ones, we get the same number as the number for pressures. And therefore, we fulfill the relationship that we want in order to have H for inversibility. But all this time, we have considered the so-called Taylor-Hood element that involves the displacements being in H1 and the pressures being again in H1. But what if we would like to consider the Crouzeix-Raviart element where displacement is in H1 but pressures are in L2? And here we are going to see, and keep the same order, sorry. And here we're going to see that it's not that simple, because for pressure being in L2, the unknowns are living within the element. They are not living at the nodes. So the degrees of freedom of each element are not shared between elements. They are only living in the interior of them. And therefore, by keeping the same order and changing the space, we bump up the number of unknowns. And what we get for the same problem where all boundaries are prescribed is that we have in total 12 unknowns for pressures, still 6 unknowns for displacements, and therefore the relationship is not fulfilled and the patch test is not passed. So in order to resolve this problem, we can bring down the approximation for pressure and now having 0 order for L2 and 1 unknown for each element. And this will eventually allow for the test to pass. But somebody could say, okay, we can bump down this, and just if we have unlimited resources, as Chris was saying earlier, we could just bump up the number of unknowns for displacements, and we would be just happy. We would never think about these problems. However, there is a deeper understanding on these formulations, and here I present the proposition presented in the both Fibretzi and Forten book that involves the inf-sup conditions. And here I'm just showing for a general case for the mixed problem that we are taking into account. U is in a general displacement are in a general U space. The solution is sought on this space, and P is sought on V space. At the moment, it's just general. And for any space chosen, this relationship has to be fulfilled, where K is a finite number that has is with respect to the mesh. But if this is fulfilled, then the solution is unique. So we can understand that depending on which choice we make for the space where P is sought, we would have different definitions of this norm, as I showed very early in the presentation. However, for displacements, as I said earlier, we always choose H1 for this formulation. And that means that depending on the choice, on the left-hand side, we have essentially the Taylor-Hood element. On the right-hand side, we have the Crouzeix-Raviart. And because these two norms are different, their relationship is different. And therefore, the choices we have to make are going to be different depending on the space that we are choosing. So it has been found that in general, Taylor-Hood elements behave better when the difference between the order of approximation is equal to 1, and for Crouzeix-Raviart, where the order of approximation is equal to 2. But there are also some restrictions depending on the number of elements that are used within the domain and on the dimensions of the problem. So regarding solving this problem, what is MoFEM bringing to solve this kind of this class of problems? So it's a mesh-oriented finite element framework. That means that we take information from the mesh in order to assign degrees of freedom and solve the problem. It's quite flexible, and the data structures can be extended quite easily for the problems that we want to solve. It brings the heterogeneous hierarchical base, and here I would like to just remind you how the standard bases that are used in literature and in many codes are the Lagrange shape functions, where for the first order we have 2 nodes and 2 shape functions. For the second order we have 3 nodes, and for each one there is a shape function corresponding to it. And therefore, going from first to second order, we need to remesh. And if we go to third order, again, we're going to have 1 extra node, 4 nodes with 4 different shape functions. Whereas for the heterogeneous hierarchical base, this is not the case. We can keep the mesh as it is. So we start with first order having 2 nodes, and for second order, we add another shape function without the need of adding a node. So the second order is a superposition of the first and the second bases. And then the third order is just adding yet another function of higher order. And this is how the shape functions look like for a 2D triangular elements. Here you can see the first order. Here you can see second and third on edges. And then from fourth order on in the volume as well. Yes, here at volume. Also, it's relatively easy to change between approximation bases, spaces, as I'm going to show later. And also, we have developed the code to be, in most cases, agnostic to the choice of having triangular elements or quadrilaterals, hexes, or tets. It handles quite efficiently and easily coded subdomains and multiple fields. And here you can see just an example of a very complicated problem where there is a need of remeshing for an immiscible fluid movement within a tube of 2 fluids. And the parallelization is quite well embedded in this code. So here you can see just a part of the code with this, that is used for solving the incompressible linear elasticity. I want just to say that we have various bases that we can choose. And this is done just by setting a particular parameter in our command line. Also, we can set fields within the mesh that we can manipulate data. And we can easily set the order of each field, even though it's not part of the actual problem. It's just a set of placeholders in order to manipulate data. Also, regarding problems that we would like to solve, we could independently add fields either within the domain or on the boundary. And you can see here an example where we, depending on a flag that we can put, we can either choose between the space L2 or H1 for a given base. And also we can change the base. So depending on the element, we can have 4 variants of this element just by changing 2 parameters. This one and this one. And finally, I'm not going to discuss a lot about this, but what I want to say is that in order to evaluate linear and bilinear forms, we have developed a set of templates, templatized operators, where we just give the name of the field and some values that are evaluated at the Gauss points, and they are templatized in order to be able to choose at the compilation time the dimension of our problem, or even the assembly that we would like to have, or even the numerical integration. So at the moment, regarding the space and the type of elements, this is quite templatized, and we don't need to have multiple implementations. We have one implementation that we can test for different cases, rather than having many implementations for different cases. And here I'm just going to show an example of how the Taylor-Hood and Crouzeix-Raviart elements behave for the case of the Cook membrane, where this is in plane strain. This is the Cook membrane with these dimensions. And on this edge, the force of 100 is applied. And then we want to monitor the displacement at this tip, the vertical displacement. And here you can see, for the simple case of the simplest case of the Taylor-Hood and the simplest case of the Crouzeix-Raviart element, how they converge towards the same solution as the number of elements increases. So regarding block solvers, I will give just a brief introduction to them. On the left-hand side, you can see the general case, not for incompressibility, but just the general case for the mixed formulation of linear elasticity. And on the right-hand side, you can see how the matrix, the system of submatrices look like on the right-hand side. This particular case is the Crouzeix-Raviart element, where the pressures are sought in L2 space. And this is important because we would see a very different picture here in case that it was a Taylor-Hood element where the pressures are sought in H1 space. It would be more or less as dense as this one, not that sparse. That is here essentially a block diagonal matrix where each block corresponds only to one element. So we could, there are emerging features that we can take into account in order to solve this system of equations more efficiently. So in the general case, regardless whether it's L2 or H1, as I said, here are the matrices, and we can use block solvers given by Petsy, where we define which is the first, the one diagonal submatrix, and which is the other one. And we can choose many different flavors of field split solvers, one of them being sure, but they involve approximate evaluation of some of the matrices. But as I said, when choosing L2 space for pressures, then there are emerging features that we can take from this structure. And there has already been published work regarding a different kind of problem, where there was an exact sure implementation when the system of unknown equation involve L2 spaces. And you can find this in this publication. What I want to say about this particular implementation is that it eventually boils down into solving a matrix that is of this sparsity and this size as the number, as the problem gets bigger and bigger, and the parallelization increases. So as I said, even if the system of equations is larger than the case of the standard linear elasticity problem, where there is only this size of the problem, there are ways to improve our solution and reduce the resources that are needed to solve this problem. So to conclude, I presented the mixed formulation for linear elasticity and what it brings to solve the incompressibility problem. The implication of the choice of order, number of elements, and somehow the type of elements was discussed. I give a glimpse of the implementation using hierarchical and heterogeneous base functions. And we just show how the two flavors of the mixed elements perform for a simple example. And there was also a brief discussion on block solvers that is quite a wide subject, and it's something that deserves, I think, more understanding and more frequency in usage from the community. So that was it, and thank you very much for your attention.